Okay, our next talk is on running novel FWI algorithms cost effectively.
Hello, everybody. Thank you very much for hosting us in this speech and for taking the time to listen to this experience. As you will notice from my accent and from my badge, I'm not from SCube. We had a last-minute change because travel from UK has been banned. So we are both from AWS, and we work closely with SCube in this project. So we are trying to represent, to the best of our ability, this project that was delivered together, and this offering that they're offering to the market. So my name is Andrea Rodolico. I work in Amazon since 4 years in HPC business development.
Hi. Can you hear me?
Yeah. Not yet, probably.
Can you hear me?
Yep.
Okay. My name is Dmitry Tishkin. I'm the partner technical lead at AWS Energy Vertical. Been in oil and gas for more than 10 years.
Excellent. And as a disclaimer, of course, we are representing a partner slide deck. So we are trying to represent their message in the best possible way. So a little bit about SCube. So SCube is a partner of AWS, but it was born as basically an implementation of the research that was led at Imperial College London about the full wave of inversion algorithms that led to a consortium called Full Wave that tries to innovate in this space. And SCube was launched in 2018 to help customers that didn't have large facilities at their disposal to try using these algorithms and improve their ability to run full waveform inversions and waveform inversion in general in their seismic processing and experiences. So the goal for, oops, sorry, wrong button. So of course, getting into the market as a startup, they were using basically the traditional methods that HPC has used for years and decades of running large-scale seismic. So they started with a code that was C, Fortran, and so had a lot of, we could call it legacy. It was not a native DevOps, super fancy code set. And it was running MPI. So it was, of course, developed in the way that most data centers offer capacity. So being able to allocate a bulk of capacity, run MPI on it, and then do the compute through the algorithms that they developed. And they had two versions of that. One that was more production code, and the other one was more like the next generation development code that was more open to create innovative approaches to that. Because basically, XWI, that is the product that SCube offers, is a combination of traditional FWI, but also augmented by other CWI, RWI, and other flavors of that allow to have a better convergence in the model towards something that is closer to reality. So basically, it's an iterative process in which you start from the modeling, and then you predict the data, you compare it to the actual field inputs, and then you update the model based on multiple techniques, and then you move it again back to the start until you have a good convergence to an optimal model. So of course, the goals of the project at the beginning was we don't want to own a data center, we want to be flexible, so they looked at AWS for the capacity part of the game, and they wanted to be able to run hundreds of jobs simultaneously without much fuss, without having to deal with a lot of complexity and reservations and so on. And of course, they wanted to be open to innovation. So they wanted to be sure that whatever they do allows them to plug in solutions when the problem comes without being stuck on specific frameworks. And it should be immediately available, so no queuing. You have to run the jobs, you spin them up, run it, and then take them down. And of course, making sure that they harvested as much value as possible in the process. So their first attempt, even before going as an independent company, was starting with an open source toolkit that we had available called CFN Cluster that was available. It was developed by a solution architect of AWS, and it allows you to spin up and down HPC cluster very quickly. So it's open source, so everybody can download it and try it. And since then, it has generated so much interest that we have developed as AWS a full product on top of it called Parallel Cluster that is actually the managed and supported version of it. But back then, they were trying to use that to scale very large in numbers. But also they wanted to use Spot because Spot is our way to offer our spare capacity at a significant discount. And so Spot was discounted between 70 and 90%, would make a big difference in the budget that was necessary for running a simulation or a campaign. And so what they did is basically pulled the code of CFN cluster, and they hacked in another tool that AWS was starting to offer at that time that is called Spot Fleet. Spot Fleet is basically a way to express infrastructure requirements through an API call. And Spot Fleet goes out and hunts for this capacity based on the parameters that you ask. So you can ask, for example, give me all C5 9 XL, which means all nodes that have a certain number of cores and a certain number of let's say, certain generation, and it will go and look for it. And then you can say, this is the minimum and maximum that I want. And so it will try to meet that goal and potentially keep that at that level. Consider that Spot is our spare capacity, so it could be impacted by interruptions. So when the spare capacity needs to be reclaimed, you can get some interruptions, even if it's a low percentage. Spot Fleet manages that and allows you to do refilling with the capacity from other areas of the data centers. So with that in mind, remember they started with an MPI workload, and they started to work on this kind of more ephemeral situation. They needed to cope with how MPI managed interruption, which, spoiler alert, is very bad. MPI was not meant to be working on interruptible capacity. So what they did is the first attempt was, let's make MPI more fault tolerant. Okay, so they put in some additional controls into the process. So if a node gets reclaimed and you get a 2-minute warning, so you have got some time to do something about it, it would enable to have a blacklist of nodes. So you start with 1,000 nodes, and then you say, OK, this one is getting reclaimed, so I will not use it for the next iteration. So they were able to create this kind of conditional MPI, which only goes to the nodes that are still alive and kicking. And so it was possible to start with a larger cluster and then shrink down a little bit through the path if some nodes got reclaimed. And of course, in the meantime, inside, they built the logic to redistribute jobs. If a node gets reclaimed, you have the ability to get the data and push it out again for the next node that becomes available. So that worked, and the initial successes were significant, and so were the feedback from the customer that made their architecture even more complex, because there were more capabilities that the customer wanted, more functionality, and so on and so forth. And now, all of a sudden, it's no longer one MPI job. It is one MPI job with a lot of different conditions in the path to actually deliver the result that was needed. And guess what? MPI didn't smell like being able to go through that kind of complexity. And so, long story short, it's not easy to add more nodes. It's not easy to manage this kind of capacity at very large scale, which they could find, but they couldn't really have a good synchronization inside of it. They decided to replace MPI. And by replacing MPI, they actually did it into a way that doesn't really rewrite the application. They just rewrote the last mile between the controller and the compute node. So whereas before, they had this very synchronized model in which they start with, I can do that. They start with the model, they deploy in even chunks to all the nodes, and then they wait for all the nodes to finish. They run the gradient, and then do it again for the second step. They move to a situation in which, all of a sudden, the model gets written down into an S3 bucket, which is our object storage capabilities. And the S3 bucket becomes like a distribution bus, with a broadcasting bus of all the data. And then they feed a thread server. So it's basically a very high-performance queuing system that allows the nodes that get pulled into the pool to immediately quickly collect one job to run, pick the data from S3, process it, write the outputs to S3, and then declare we're good, we can move on. This allows basically to have as many new spot workers and as many spot reclaims as you want. The architecture just manage that. Spot reclaim, quick rerun of the job, and you can continue going forward. And if you want something faster, you can enlarge the pool. If you're OK, you can keep it the same. So it's very, very flexible as an architecture. And of course, second step goes in the same way. It fills, again, the broadcasting, let's say, layer and does the same kind of logic. So this was working in this kind of master and worker play in a very, very efficient way. And the interesting thing is that they could even get rid of one of the bottlenecks in that previous architecture, because when you look at MPI, the master node was the one that was actually distributing data back and forth. So the network of that component is important during the whole computation. With S3, you can have multiple terabytes per second of concurrent access, performance, and bandwidth. So you don't have that bottleneck. The minute all the data is there, you can put as many nodes as you want to read and write as many times as you want, and you have a very, very scalable infrastructure. So with that, of course, they were able to do this, to run this architecture at a very high scale. And we started looking at that kind of complex architecture of their application, and they've seen opportunities coming from re-engineering the communication bus. One of the things that they noticed is that the logs that are produced at every step of the way get produced into S3. So S3 is a single source of truth for all of the outputs of that kind of environment. And the interesting part is that S3 is an active storage. So the minute a new file is written, you can create an event, and that event can be trigger some other function, for example, a serverless function that can analyze the log and can detect on the fly whether there is something like performance data in the log or some warning about the overall convergence of the algorithms, or if there are some performance metrics, analytics can be done on the fly, and they can even trigger other jobs. So if there is additional processing that you want to do based on the kind of logs that they get, they can do that in real time. So this basically allowed every node to write the log into a central repository through CloudWatch log and generate automatically some processing via serverless. So they didn't need an HPC cluster or any HPC planning for that. It was all built with this serverless environment. And so even if this kind of architecture today would be probably consolidated into a single event bridge because it performs all those functions, it was a great way to kind of start simplifying the architecture and focusing on implementation of new features without having to touch the core code that is the computing angle. So this allowed them to produce a separate value that was all the analytics and all the monitoring could be offered as a web environment that was running side by side to the HPC environment. And so you can easily track, for example, the progress of the model in the system. And so you can do very quick visual comparison between the actual field and the prediction that you have. And so very quickly you can compare these kind of things through a browser. You don't have to install anything. The team in the UK could collaborate with the customers and look together at the same environment and make sure that all the knowledge was shared. And you could do that across different kind of visualization angles. So for many of you, this might mean a lot of how you can understand what is the most accurate model based on contrast comparison and so on and so forth. And so these kind of things were made possible to this kind of continuous update of data sets through the S3 integration. So these are some other examples of how applying this kind of iterative model This one is a traditional FWI, so the deduction of these kind of models has been not particularly good because it's a salt-flooded region, so it has very different convergence parameters. And so instead of having this kind of thing, by having the ability to, oops, sorry, wrong direction, having the ability to have this iterative process, it was able to actually come to a much more accurate representation of reality, both in horizontal and vertical view. You can see there's a major difference between this and this kind of very inaccurate modeling. So back to the whole experience. There's one more thing that was very interesting during the development, is that one thing is doing the same things in the same way but more elastically. Another thing is taking down also more of the Amdahl law challenges. Because in this process, there is still this gradient calculations that is a very, very meaty blocking step. And so that step alone was very significant in the processing, because it would take something like half an hour on a typical model using the same CPUs that we're using for the normal FWI step. And so they tested different things. On AWS, you can spin up GPUs of different sizes. You can even have FPGAs. You can play with stuff. And so they tried to see if that kind of gradient application could be implemented better by GPUs, and the impact was really significant. So GPUs have saved the day in this case, and allowed to move from half an hour to 1 to 2 minutes. So obviously, there was an interest to understand what was the best way to implement GPUs. So what happened, the short of that is they just made sure that whenever you get near the moment when the gradient needs to be calculated, there is a notification. You remember, you can count how many logs are coming in, how many successful jobs. When there is enough that come in that suggest it's almost time to do the gradient, you launch a new 8 GPU instance out of nowhere, and then you quickly calculate the constraint gradient. Takes a few seconds, minutes, and then you just terminate the GPU instance, and off you go with your work. So this is the fastest way they could find to do this kind of step theoretically. So they went on and tested it onto real cases, and these are more or less the numbers we're talking about. So if with a project of 500 megabyte of model and the 1 terabyte of subsample data, so the size is what it is, but it seems that gives you some metric. They basically running on basically 8 core nodes. They were able to run for about 30 minutes per job, and the total cost of 100 iterations for 50 hours was about $3,900. So that's the kind of cost of running, FWI on this project on AWS. Of course, when it comes to the implementation of that, you have a different model if you go with CPUs. That would have taken 30 hours additional time to do the gradient with the CPU, an additional cost of $2.3 kilodollars. They also considered using a GPU instance as a head node, so the GPU would always be on, and they would be able to use it when needed for the gradient calculation. That would have just completely slashed the additional time from 30 hours to 1 hour, and the cost would be still lower, but still material to the cost of the project. And so they designed this more optimized scenario in which, by running on demand the GPU instances, you go down to 1 hour of delta and $50 of cost. So would it be worth to spend a good steak dinner on 30 hours of savings? Probably yes. So that's the kind of things that running elastically on a framework works. So short summary, this kind of experience showed how from a traditional MPI FWI implementation, it was able to go and implement a completely different but relatively simple code changes made it possible. And this enabled a complete new opportunity to improve the algorithms. And they are thinking about going much larger scale, millions of cores deployed, having the ability to, for example, implement machine learning-based optimizations throughout the process, and of course, real-time verification of QC results with parallel jobs and other areas. So we are on time right now?
You got 9 seconds.
9 seconds.
Perfect.
Okay, time for maybe 1 or 2 quick questions.
And Dmitry will help me on the technical questions if they're...
Yeah, I'll answer your questions.
Hey, Andrea, great talk. You mentioned that right when the gradient's about to be calculated, you then spin up a GPU instance. I'm just wondering, what is the largest GPU instance that you've consumed on this? Has it been scaled out to a larger workload that's consumed maybe in the hundreds?
At this stage, it was running on a single 8 GPU instance.
It was a single instance. We didn't see a point yet going into multi-instance yet because it's a single instance, which is 4x large, I believe, gave us very good results, right? It's just 1 minute.
But do you see it scaling out linearly with the size of the data and the gradient?
Without MPI, it should scale out linearly. We'll do more tests with the bigger data sets later. Yeah.
Thank you.
Okay, maybe a quick one right at the back.
Yeah, very nice presentation. Thank you. On the stuff about the GPU, was that the total clock time that elapsed time that you saw the advantage, or is that just the computation time? Because obviously it takes time for the data to be loaded to the memory and back, right? The GPU?
It's both. It's both. Because this solution reads natively from S3, right? So it reads natively from object storage in parallel, and it's capable of creating a large throughput on a single node, right? So we're talking about terabytes per second from S3, right? So it's one node, but it can scale more. And
yeah, but my question was
both
really...
reading time and computation time, right?
Yeah, but your advantage, was it just purely computation, or it was the clock?
It's both. To answer your questions, both. Yeah.
Thank you.
So basically,
there is one hidden thing, that's a spin-up time. The spin-up time is not included because we spin up instances in advance, and a spin-up takes 1 to 2 minutes itself, right? When you start the instance from the start to where it's ready to go.
And the instances we are talking about have 100 gigabit connectivity to the backbone, so they have a very fast connectivity to S3. They have local storage, so you can preload some data that is already available in S3. So you can imagine that you can optimize the bandwidth to really be, saturating the 8 GPUs in the best possible way.
Okay, I think that's all we have time for on this one. Thank you very much.